All right, section 11.2. We're going to talk about, we just got done talking about intermolecular forces and the three types of intermolecular forces. In the order of strength, the weakest is London dispersion, followed by dipole-dipole, followed by hydrogen bonding. Now, each one of these intermolecular forces is affected by physical properties. And we're going to talk about the couple of physical properties that are affected by these intermolecular forces. And the first is viscosity. Now, what is viscosity? Viscosity is the ability for a liquid to flow. Now, viscosity increases with stronger intermolecular forces and decreases with high temperature. So if you think of liquids, what is a liquid that is very hard to pour or has what we call a low viscosity? All right, when I think of something, I think of molasses. If you've ever cooked with molasses, you've ever heard as slow as molasses in January, molasses is really hard to pour. It's real clumpy, kind of almost when you pour it out. So it doesn't flow very well. So that has a low viscosity. Likewise, like motor oil. Motor oil has a very high viscosity simply because it pours very fast. It's a very fast flowing fluid. So viscosity is something that can be affected by intermolecular forces. Another thing is surface tension. Surface tension results from the force on the fluid at the surface of the fluid. So water has a great surface tension. Why does water have a great surface tension? Because water has hydrogen bonding, and hydrogen bonding, remember, is the strongest of those three intermolecular forces. So we have viscosity, we have surface tension. One additional thing which these intermolecular forces can affect are phase changes in the amount of heat it takes to have that substance go through a phase change. Now, I'm not going to go through this example in the notes. I'm going to go through it on the worksheet in class simply because it's going to take 5 to 10 minutes to go through it in class. But what we're going to talk about is phase change and the amount of heat required to go through a phase change. We're going to study thermodynamics. We're going to bring this thermodynamics equation back, which we learned earlier in the year. The Q is equal to M times C times change in T. We're going to apply that to phase changes. The important thing to note is that phase changes require more heat if the bonds are stronger. So if you have higher intermolecular forces, it's going to take more heat for that phase change to occur. Now, one thing that we are going to add, and I'll explain in class a little bit more too, is the idea of these heats of change of phase. So we're going to talk about three types of heats, so-called. We're going to talk about HF, which is the heat of fusion or the enthalpy of fusion. That's the amount of energy required to go strictly from a solid to a liquid. So keep that in mind. We're going to talk about the heat of vaporization, which is the amount of heat that requires to go from a liquid to a gas. Then we're going to talk about the heat of sublimation, which is the amount of heat that goes from required to go from a solid to a gas. Now, one thing to note here is if we look at the change of state, we have what we call kind of a phase graph here, kind of showing the temperature versus heat added for phase change. Whenever you go through a phase change, it takes energy to go from just strictly have a phase change. So it takes energy to go from a solid to a liquid. Then it takes energy to go from a liquid to a gas and vice versa. So if we follow this chart, and what we're going to focus on in class using this Q is equal to M times C times change in T, is this. If I wanted to know the total amount of heat required to melt ice into a steam, what I would have to figure out is I would have to figure out if my ice started at negative 25. I would have to figure out my Q for M times C times change in T, taking that ice from negative 25 to 0. Then I would need to add my heat of fusion, which is how much energy does it take to go from a solid to a liquid. Then I would use my Q equation again to figure out Right? How much heat does it take required to go from 0 degrees to 100 degrees Celsius for water? Then I would need to add in my heat of vaporization. How much does it take to go from a liquid to a gas for water? So the key thing here, and we'll explain this more in class, is that you simply can't go from negative 25 to 100 using that Q equation. You also need to factor in your heats of fusion, your heats of vaporization, your heats of sublimation, depending upon where your phase change is happening. So we'll talk about that more in class. So that's kind of a key thing there. Vapor pressure. We've talked about viscosity. We've talked about surface tension. Next thing affected by intermolecular forces is vapor pressure. Now, what does vapor pressure affect? As there's more molecules escape the liquid, the pressure increases. What does vapor pressure affect within a liquid, though? It affects boiling. The boiling point of any liquid is the temperature at which the vapor pressure equals the atmospheric pressure. Now, the normal boiling point is the temperature at which the vapor pressure is at 760 degrees torr. Now, last year in chemistry, we talked about a potential question of, is it possible to boil water at 40 degrees Celsius? And the answer to that question is yes. Well, how do you do that? Well, if you can lower the atmospheric pressure, you can lower the vapor pressure, and therefore you can boil at 40 degrees Celsius. For example, if you look at this graph here, it has water. Water will boil at 40 degrees Celsius at a pressure of about 50 torr, which is not a lot, but it's possible. So kind of keep that in mind. The boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. So if we have higher intermolecular forces, it's going to result in a higher vapor pressure, which is going to result in a higher boiling point. So kind of keep that in mind. That's how vapor pressure can get affected. Now, I'm not going to focus on the natural law graphs. We're not going to focus a lot on that. Last thing that we need to focus on for 11.2 is phase diagrams. And we had phase diagrams last year. Very briefly, we talked about them. You're going to see phase diagrams come into play here on the AP test in multiple choice questions. So just a handful of multiple choice questions, but these are very simple questions to nail. So it's a very easy concept. A phase diagram is going to show pressure and temperature of a substance, and at a particular pressure or temperature, it's going to show whether it's a solid, a liquid, or a gas. So you can see here, we have a solid, a liquid, or a gas. And we have a triple point. Now remember, the triple point kind of explains it's all three phases of matter at one exact pressure and temperature. Other than that, it doesn't exist. So, what does this phase diagram tell us? Well, it tells us a handful of things. It tells us T, which is the triple point, which tells us all three phases of matter are in equilibrium. And it tells us the critical point where you can no longer tell the difference between a vapor and a liquid. So you have your T and you have your C. What else does it tell us? Along each point is the boiling point. So for example, right here, anywhere between a liquid and a gas, we're talking about our vaporization or boiling point and condensation based on a particular pressure. If we go between a liquid and a solid, we are looking at the melting point and freezing point. So this line going all the way up here is the difference between a solid and liquid. So anywhere on this point is the melting point or freezing point for this particular liquid. So it's going to ask you, where's the solid, where's the liquid, where's the gas? Remember, the higher the temperature, it's good. Any substance, the higher the temperature is most likely to exist as a gas. So if you look at the bottom of this graph here, temperature, as we go across the graph here, we're going to go from solid to liquid to gas, because as we increase temperature, it's most likely that something is a gas. Here is this phase diagram for water. Very clear. Solid, liquid, gas. Right? Very clear melting, freezing point. It stays the same regardless of pressure. All right. Liquid, the boiling point changes because of pressure a little bit, but not a whole lot. If we look at a phase diagram for carbon dioxide, you can see it's slightly different. We have the triple point. You can see where sublimation occurs on this green line here, though, as you go from a solid to a gas. So we are going to practice a lot with phase diagrams, and your questions are going to be, you're going to have a couple questions on phase diagrams in the quiz. But they're pretty simple to master, and there's something which on the AP test, you're going to get a handful of questions, and you should be able to nail these questions on the AP test. So that is the end of section 11.2, and it is also the end of chapter 11.